Cool. Hey, how's everyone going? Hey, thanks for coming. So my name's Dietrich Featherston. Thanks for sticking around for this talk. I had a lot of fun putting it together, so I hope to return the favor and make it enjoyable for everyone else too. So a little bit about me. So previously I built Boundaries historical database. It was named after a competitive eater named Kobayashi. I've had a few people ask me about this, so I'll put some reference to this. I have references that I'll give you at the end if you want to read more about that. Right now I build analytics infrastructure at GitHub. And I've been at GitHub about 2 years right now, building analytical infrastructure. And at the time that I joined, so 2 years ago, GitHub already had kind of a strong product, strong presence and whatnot. So one of the goals of the team was to kind of come in and kind of add analytical rigor to an already kind of strong and whatnot company. So what we had to figure out was we kind of had to figure out how to structure ourselves. We had to figure out how to come in and be effective. And so kind of one of what we've kind of arrived at right now is that the analytical team at GitHub, we kind of serve two different purposes. We are a services team. So we are a place where all of the other teams at GitHub, marketing, sales, billing, product, even the systems team, they can externalize a lot of their analytical problem solving to us, and we can help move some of that stuff forward. We're also an infrastructure team, so we build, manage, operate all of our own infrastructure to do these things. And something that we've kind of based a lot of our actions on is this idea of question-driven development. So we kind of think of analytics at GitHub as a question-motivated process. We start with the questions, and we start with trying to have a deep understanding of what the needs of the various teams are at GitHub, and then kind of do whatever we have to answer those questions, right? And that involves a lot of ETL stuff, a lot of one-off scripts, a lot of just kind of awk sed, number crunching, doing stuff in R, just all kinds of stuff like that. But after we started answering enough of these questions, a lot of patterns started to emerge. And this is what allowed us to start actually building infrastructure to help the team move faster and faster and faster. So what I thought I would do is, so a lot of this talk is, I'm not going to be trying to sell you on any specific technologies or any specific infrastructure, but what I do want to talk about is some of the lessons that we've learned in building out this team. And we're still learning these lessons because the team is relatively young, as I said. But I want to kind of toe a balance between just talking about a bunch of GitHub-specific problems and talking about things that you can actually take away from here and apply and use your imagination on. So I thought I would start with a couple of anecdotes. And if we're going to talk about anecdotes, I thought it'd be cool to talk about music first, because music makes people happy, and we like talking about music, and music's fun. So let's do a music example. So what do musical scales being played on a violin look like? This might be the first thing that comes to mind, right? But this is not what musical scales being played on a violin look like. This is what we read. If you're a violinist, this is what you might read in order to know what to play, but this is not actually what comes out the other end of the instrument. The reality looks something a little bit more like this. Does anyone know what this is? A spectrogram. So as far as how to read a spectrogram, so we have time extending from left to right, and then we have pitch of sound or frequency going from bottom to the top. And then at the intersection of these two things, the volume of that frequency at that time, we intensify the color to denote lots of sound presence at that pitch. So what does this structure tell us about what's actually coming out of the instrument? Well, first of all, I said we're going to sequentially play a series of notes on a violin. So these bars, can everyone see those okay? There's a series of vertical bars that extend from left to right, and those are the actual individual notes being played over time. So that's some of the structure that we can kind of pick out really easily. But then if we see, there are all these kind of horizontal bandings that go up and down too. So if you look slightly, it's really subtle, but these are at different kind of vertical positions. But if you look at this bass here, this is the actual, when we look back at the sheet music, this is the actual note that's being played by the violinist. And then everything above that is what's known as the timbre. So this is what gives the note depth, complexity. This is how the signature of and these are the harmonic frequencies given off by the fact that the violin is a stringed instrument. And again, outside the scope of this talk, but the signature of these harmonics that are given off are the timbre of the instrument. And this is how our ears are able to distinguish between me humming a pitch, a violin playing a middle C, a piano playing a middle C, or a middle C coming out of an old Atari or something. So this is essentially how our ears distinguish that and classify that sound. And then if we zoom in, we can start to tell more of a story about the structure too. So like right in here, we see a little blip that continues all the way up the harmonics. And that might be, I don't know, it might be fingers being moved in preparation to go to the next note or something like that. And then we see a lot of background noise here between the harmonics, and that could be, I don't know, it might be artifacts of the bow making against the string, or it could even be recording artifacts, right? The point being, like, we could sit here and we could analyze this, and we could tell a story about what's going on here, and I could probably talk about it the whole hour, right? And then if we look at this, I think you can still see some of the structure here, right? This is an entire orchestra being mic'd, and we're seeing the spectrogram for the entire orchestra, all of the instruments being aggregated together into one view. What we see here is there's a lot of information loss. There's still a lot of structure. You can still make out some of these harmonic vertical bandings here, but it's a lot more difficult to tell what's going on. And this is what's known as aggregation. This is information loss. It's harder to distinguish the actual structure in the message. So the reason I went through that example was to prime you for this next example, which is what do service latencies look like? So you might think of service latencies as looking something like this, like if you're plotting 90th percentile response times, something like that. This is not actually what response times look like in a real system. In fact, if we replace frequency with latency, we can actually see some of the same structure that we saw when we were looking at sound being played over time. So does this kind of make sense? So we can start to pick this apart too. We can start to get a mental model of how our system is behaving too by looking at the structure of the response time over time. So we see a lot of, the color doesn't stick out as well as I'd like here, but anyway, so you can see a lot of low, like the darkness is more and the lightness is fewer requests. So, but anyway, so you see along the bottom, we see lots of low latency requests. So that's probably a good thing. But then we see this big arc that kind of comes across the top as well. And so how might we try to explain the differences in these types of requests, right? Well, so one way to explain this might be that these are reads of an API and these are writes, and our writes are just more expensive. Another way to explain this might be that these are cache hits and these are cache misses, and this is the time it takes to fault a page into memory to actually perform a read. Whatever the case there, there's some more structure we could pick apart too. Lots of outliers up here, which we'd have to explain. But then if you kind of squint your eyes, there actually looks like there's two arcs here that kind of track each other. And it might be interesting to try to explain what that is too. But the point is that there's a moral to this story, right? And the moral is that aggregation is information loss. And it's useful, it's not bad, but it is information loss. And when we think about latencies in our systems, they are distributions over time, aggregated over increasingly small time windows. They're not point-in-time measurements necessarily. They're not a commodity price or something like that. They're actually a distribution of values that we want to track. And I said all of that not to say that you shouldn't track tail latencies because you lose information to aggregate those numbers up, but just that there is information loss there. And there's a lot of structure in there. And the process of going through and looking at this structure and trying to explain it is a tremendous boon to your mental model of how your systems are actually performing, in production in real time. So, so tail latencies are good. Use them, control them, whatnot. I just wanted to be super clear on that. So that's one anecdote. I've got one more, and then we'll go on to some other stuff. So in 1872, this was after Leland Stanford was the governor of California, but before he founded Stanford University. He took a position on a popular question of the day, which was, when a horse is in full gallop, do all 4 feet of the horse leave the ground at the same time at any given point in the gallop? And this seems like kind of an odd thing to try to answer, but at this time, it's something like a horse in gallop is something that happens so fast that it's not obvious by watching whether or not all 4 feet are leaving the ground. And camera shutters and human reaction time are too slow to actually prove what's going on. So what Muybridge did was he devised a super fast camera shutter in order to take pictures of anything. He did animal studies and other motion studies. It was able to put together this series of images, right? And we can see here, like, this is slowed way down, but you can kind of start to see that, the feet of the horse are leaving the ground. But then if you break out the individual frames and look closely, you can actually see in those 2 frames up there, we have 2 continuous consecutive frames where the feet of the horse are actually off the ground. So it's actually proven at this point, right? And what's interesting is that before this time, I think if you looked at artist paintings of horses in motion and whatnot, they all always showed 1 foot on the ground because we didn't really know that this actually happened. In order to produce these, he had to develop a shutter that took pictures of 25 times a second, which is a lot more than anyone had done before. So with that priming out of the way, if I've been transferring 5 gigabits a second over a 10 gig connection for a full minute, is my switch capacity being exceeded? You have no idea. In fact, it might even not occur to you that this is the case, right? If you're looking at a typical graphite chart of throughput or something like that, or you're having network errors, and you see these little 1-minute integrals of throughput over a switch, then you would see it at 50% capacity. You might not even give that a second thought, right? But if you take pictures and you integrate over smaller and smaller time periods, you may start to see things capping out at the capacity. And if you essentially integrate the curve of everything above capacity, that is throughput that, in the case of TCP, would have to be retransmitted later, or in the case of UDP, you just lose those datagrams, right? So we have to take pictures faster and faster and faster to actually see kind of what's going on. So the moral of this one is measure as often as possible. Otherwise, you can actually lose information. And to be particularly conscious of information loss in visuals, especially, and this I'm going to pick on graphite a couple of times in this talk, but especially when your pixel resolution is lower than the resolution of your data, you necessarily lose a lot of precision when actually doing that. So, and another good example of this was that at Boundary we did a ton of GC tuning on our streaming system. And we got to the point where we had graphite charts showing the old generation JVM heap usage. It would go up, collect down, kind of the classical healthy or sometimes not so healthy GC behavior. And we got to the point where we're like, well, some of the cycles were happening fast enough that we lost information in terms of what the old gen would grow to and what would collect down to. So we ended up having to read a lot of GC logs to get the exact measurements, build our own visuals, and use some other visuals to actually see what was really happening here. So those are some anecdotes. And so I wanted to move on and talk a little about the mechanics of data movement. And specifically, I mentioned earlier that we're starting to build more and more of our own analytics infrastructure at GitHub. And I want to talk a little bit about what we've learned here and specifically how to think about the different phases of that pipeline. I'm going to mention a few specific technologies, but this is more about kind of how to think about the problem. So, but some of the motivation, right? We live at a time we have lots of We have lots of vendors that we can externalize some of our analytical problem solving to. We have things like Google Analytics and tons of other vendors. And they can solve, a huge part of our of the analytical problems that can come out of an organization, right? And we should totally use them, right? Definitely use stuff like that if it's cost effective, and that's good. But be aware, because at some point in time, and as the needs of your organization grow, you can start to recognize that your mode of thinking about your analytical problems and your questions, they start to become shaped by these tools. And that's a good sign that, okay, we might need to back out. You might need to build some of your own infrastructure or something else. And my friend Ben Lindsay said this fairly well: act like you know my website, act like you know. And it was just kind of a tongue-in-cheek reference to these websites that claim to do a lot of this work for you. Because it's kind of tempting to think about this, about our analytical workloads in terms of this kind of 80-20 equation, right? Where we think we can get 80% of the value for just kind of 20% of the effort, and that's really kind of only part of the equation, right? So here's some pseudo math, but really what we should expect to see is that really what I'm trying to get across here is that as your organization is relatively young, some of these problems are easier to solve, easier to externalize. But as your needs become more and more and more specific to the actual problems you're trying to solve, the actual products that you're building, you should expect to put in an unbounded amount of effort to collecting the right data and getting the questions out that you really need to answer. And then if you actually integrate that curve, you get infinity, because there's no way to collect everything. Because it's a sad world. The universe is under no obligation to be observable. The universe doesn't really have our back when it comes to this kind of thing. We have to just put our back into it and engineer the tooling that we need to measure. And it kind of gets worse because our tools don't really help us here. And what I mean by that is some examples. So the database backing your product holds live transactional data, but it doesn't really help you understand how that user behavior changes over time, right? So when if I write an insert into a MySQL database or something, or an update or whatever, that's destructive. I'm destroying the state of that record as it was, and I'm writing a new value into place. And I don't really have it. Like, if I want to go back and see what the state of the world was yesterday, what do you have to do, right? You have to go load up an old snapshot and then try to see what the value was then. So the database itself, that's not this particular shape of database. That's not its job. It's not its job to tell you how things have trended over time. And similarly, we have routers and networking devices and whatnot, and these things move data from place to place. But they don't really help you understand what the communication patterns in a distributed system look like. We have to build our own stuff to be able to tell that. And this is an example I'm kind of fond of too, like an aircraft, right? Like, just the fact that you have built a thing, you've attached propulsion to a device which can carry people through the air. Just the fact that you've built that thing doesn't mean that when it fails, it will tell you why and the precipitating state that led to that failure. We have to engineer systems to put on board that thing to help us understand that if there's some kind of event. So, this is what I just said here. Like, if you actually look at the history of these onboard flight recording devices, it's pretty interesting, because like in the early 40s is when the Civil Aeronautics Board issued the first round of regulation to put altitude, vertical acceleration, airspeed, to actually measure these things and put them on board, so that in the event of a crash, we could go back and do some accident analysis. So that happened in the early 40s. Then a little thing called World War II happened, and a lot of civilian resources got redirected to war efforts. So this got put on hold, and they rescinded the regulation. Then later after the war, 1947, there was still no suitable technology for actually measuring this stuff, so they had to pull the regulation again. In fact, it wasn't until 1957, after determining that there actually was suitable technology to measure this stuff, that we could put it in place. And it was 1958. So it took the better part of 20 years from the point of instituting regulation, realizing that there was this hugely important thing to measure. It took the better part of 20 years before it was actually on an airplane and collecting data and helping us figure out, why something crashed, why there was a failure. So, and this is like if you strip away all the these little black boxes, if you actually strip away all of the outside and all the stuff that you actually see, all the flashy coding and everything, you're left with something that looks a little bit like this. And I like to kind of break this down in terms of, I think there's a lot we can learn from looking at each of these phases and then tying that back to what the job of really great analytics infrastructure looks like. So that's what I'm going to flatten this list, work it from head to tail, and then see what we can learn from each of these phases. So we kind of go from collection. So on the far left here, we have, this is where you actually have devices which are measuring altitude, airspeed, stuff like that. And then they are emitting some kind of electrical signal that lies on some range of voltages, right? And then you have these little adapters that they'll take that input voltage and then map it onto a standard voltage. And then that goes down to these scribes, which take that standard voltage and then carve, it's almost like a, what do you call them, the seismograms that we use to record earthquake activity, right? So that will actually carve data onto this scrolling piece of foil. And I think this foil holds about 6 hours, so it's like a big kind of roll of film, right? So you have like 6 hours of these scribes, right? And then the whole point of this is that once you actually once you actually etch the data into this scrolling piece of foil, you've got a nice thing that you can unroll, right? So you can have, you lay it out and you can actually start looking at it and you can correlate these numbers next to each other and try to do some kind of analysis of what happened.
What pulls the foil?
What's that? What pulls the foil? If I understand correctly, it sits on a, it's electrically driven and it has some number of inches per hour. There's just a very slow gear that will just turn this, so that as the seismogram-like things are actually etching on the foil, they're not moving anything. They're just moving up and down, and it's something else that's pulling the foil through and creating the carving. So does that make sense? Okay, cool. So as far as the collection phase, this is kind of a lot of what we talked about so far. But like I said, universe, totally indifferent to our pain. It does not have our back and it owes us nothing. So do whatever it takes to measure this stuff. Sometimes it's cost prohibitive to measure the stuff that we want. As we learned with this, the whole design of the system in the first place, it didn't engineer itself on principle. We had to really put our back into it and try for years and years to get it right. And it was hard, so we just didn't get to have it yet. But anyway, so be ready to put in lots of effort here. And if you learn nothing else from this talk, it's just to do whatever it takes here to measure the stuff that you care about. But in all seriousness, there is actually some practical advice that I can offer that I think is useful. So in terms of collecting good events, as far as what should actually be contained in these events is you want to collect as much context as possible, or really as much context as is feasible. And especially when that context is expensive to retrieve later, or it can change out from underneath you. And to give a couple of examples, like one of the things we want to do is track language popularity over time at GitHub. So at the time that someone stars a repo or watches a repository, We want to know what the language makeup of that repository was at the time that it was started, because that's something that can actually change over time, right? So we would know that it was like 20% shell, 40% Java, and then what's left? Then 40% Ruby or something, right? So we want to know that breakdown so that once we're scoring language popularity downstream, once we're actually consuming this data, we know what the language, how to rank that thing and how to have it affect language popularity at the time it was recorded, not at the time that we're actually doing the analysis. So that's super important. And similarly, if you actually want to find out the language breakdown of a particular diff, like if we're going to collect an event every time someone pushes code up to GitHub, then we want to have all of that data in all the stuff we care about, all the metrics in the event itself. I don't want to have to go back and dig into Git storage for every single thing, and then to reconstitute this and compute the statistics coming out the other end. Also, I just want to mention this really briefly. Be sensitive to personally identifiable information when you're collecting events. I'm not a lawyer, so I'm not going to really advise you on this super in detail, but just kind of know the rules there and kind of look into first party, second party, third party collectors and kind of know what you fall into there, know what's cool to collect and what isn't. So collect as frequently as feasible. Just like if we think back to the Moody Bridge example of the trotting horse, collect lots, collect as often as you possibly can, really. And then also don't wait. Like when you're collecting events, don't wait until you have some kind of perfect analytical system. Go ahead and start collecting early, because like the message loss rate right now is 100% before you start collecting anything. So be aware of that, right? So you'll be happy once you actually you're growing and you're maturing your analytics infrastructure. You'll be glad you have some data to go train it on and actually go see how you're doing. So yeah, start early, even if it's not perfect. And as far as specifically collecting events about specific systems, I've mentioned networking devices and I mentioned databases. So I want to talk about that a little bit as well. So libpcap is a really nice C library that lets you inspect packet headers and pull all kinds of interesting stuff out and determine what's going on in your network. You can see, you can look at a packet header and see like what IP address it's coming from and what port, and then what port it's going through and what IP address. You can pull out all kinds of other statistics like the size of the packet and then aggregate that over time and figure out throughput over various devices. You can do all kinds of cool stuff here. And that's essentially how we built the meter at Boundary. And we were able to take that and put together a big distributed picture of like entire, we were able to put together comprehensive communication patterns for an entire distributed system. So that's a good place to start if you care about low-level network monitoring. As far as, so I mentioned databases and stuff. So we do a lot of active record stuff at GitHub. So we have a big Rails stack and an active record piece, and I mentioned that as we, one of the problems we've come into when we have, we'll oftentimes have a question we want to answer that we don't have the data for because the database where we hold it is destructive and then information actually gets destroyed, so we can't go back and look easily. So one of the things we're doing is we're starting to instrument our active record models in order to collect context before any of that data actually gets changed. And a thing to be aware of here, especially if you have, it's Ruby, right? So if you have like a unicorn-based runtime or whatnot, you don't want to block those unicorns, right? So since I've advised, we talked about adding lots of context to these events, it takes time to collect that context and add it to the event, right? And that's time that you don't necessarily want to start escalating your web response times in order to just collect these events, right? So beware that context collection will accrue additional latency, and to try to mitigate that if you can. One thing we do is we have a little C daemon that runs on all of our front-end machines, and the unicorns can just write over a local Unix socket. Then that thing can queue those events up, and then it has dedicated threads for jettisoning that stuff off to our collector. So the only latency we accrue on our webheads is just how long it takes to send that event over a Unix socket. and then it handles all of the latency of pushing that synchronously up to our collector. So that's a little trick you can use if you have a GIL'd runtime of sorts. But as far as instrumenting actual active record models, I am not a Rails developer. I am not a Rails expert, so there may be better ways to do that, but that's a way that we found to be pretty useful. Finally here too, you can write little local daemons to pull iostat, iotop, basically any kind of Unix system utility that can give you some measurement or number. Like how many people have ever written a little Perl, like you're dissatisfied with the granularity you get from, say, Graphite in terms of looking at a system metric like disk util. So you write a little Perl script that just pulls that number as fast as you can so you can see what the real pattern is. We do that all the time, right? So you can take that a step further and actually write little daemons that do that for you and push those events up to a centralized place so that you can do that all the time instead of just kind of writing these little one-off scripts. So that's all I really have to say about the collection piece, and I think that's the most that's probably where we spent a good deal of time trying to get that nailed down. But there are important things to take care of. Like even if you're collecting great events, there are really important things to take into consideration to make sure you can really make use of them later. So this next step I like to call the normalization step. This is kind of where you make everything look like everything else. Not exactly, because you still have types, but you want to think hard about some standard ways of representing certain types of data, and specifically some kind of predictable event structure. You want to differentiate, first and foremost, you want to differentiate between your dimensions and the metrics that you're collecting. Metrics being quantities, number of page views, the latency of a request that you measured, any quantifiable thing, those are your metrics. And then dimensions, these are the things that help you avoid the problem we ran into when we looked at the spectrogram of the orchestra, right? Everything was just kind of crunched together, and by having everything aggregated together, we lost information about what instrument was which, right? Collecting lots of dimensions, and this is usually where your context collection comes in. But by having lots of dimensions, you avoid some of that, and you can start drilling down and figuring out what your hidden variables are that affect the structure of the metrics that you're seeing. So dimensions are things like user ID, time, week of month, anything categorical that you can think of. Event type, it's a big one, definitely record that. So this is especially important. So it's important in static languages, statically typed languages too, like even if you're using something like protobufs to represent your events in flow. It's still good to have some kind of common mode of referencing, say, IP addresses and things like this that are going to be very commonly represented in your events. But it's especially important if you're using a dynamic language for this stuff. You want to make sure that because you don't necessarily have IntelliSense and code completion for a lot of that stuff. You want to make sure that you have really consistent ways of representing the stuff. Like IP addresses always have the same property name, etc. And that's going to come in really handy here in a second. And yeah, so think hard about your type systems. And so once you've done that, we've collected the data, we've normalized it to a point that our events have some kind of predictable structure. And if we've done this right, this kind of spans all of the event collection across our organization, right? And we'll talk about that more in a second. But at this point, you want to record data to the log. You want to record it. So we've got the events, we've created some predictable structure, and now we want to record it so that we can have things actually consume it. And as far as event recording, the actual API doesn't have to be super exciting. You can just have an HTTP API, and if your throughput is low enough, or if you can use HTTP, this is a good place to start. You can just post JSON events to a collector, and then that's fine. If you need to do something more sophisticated, the same kind of semantics apply. I think you're just kind of batch pushing events to some kind of endpoint in your system. As far as storage, I've seen people get this wrong a lot, I think, and I would actually say that using a queue for this kind of data is actually wrong. And reason being that if you actually load events into a queue, you're stuck with this model of having a single consumer, and it's harder to keep one consumer from blocking others, and then kind of fanning these events out to multiple things that need to do work on this event stream. So use something like Kafka. I know I'm coming here not like trying to sell specific technologies, but Kafka is spectacular at this kind of thing. So Kafka is a data log, not a queue. And you can use, and the nice thing about recording your event stream in Kafka is that you can have multiple consumers of that stream doing different kinds of work and not interfering with each other, because each one of them tracks their own offset into the log. So you can have hundreds of these things, and that's fine. It scales really nicely to handle that. And then they all kind of coordinate in Zookeeper and track their offsets there, so you don't have to worry about a lot of coordination costs there. So one of the, actually the first thing we did at GitHub in building our infrastructure is that whatever system you're storing these events in transit, wherever you're kind of recording them durably to, they're not going to stay there forever, right? This isn't a system, that's not the system of record, this is just a event log, right? So the first thing we did was we wrote a dedicated consumer that just batches up blocks of this data and then uploads them to S3. And we do that in a format that allows us to run Hive queries over that data. And we even do some uploading of TSV data, so I can directly load files in S3 into Redshift, and then I can run really amazingly complex queries on that. So just by virtue of taking your event stream, batching up that data, and then uploading it to S3 in a predictable format, you can actually get a tremendous head start on doing a lot of really ad hoc analytical work over this whole event stream. So we use Hive, and starting to use Redshift a little bit too. And so as far as recording, there's one other thing I wanted to touch on. So if you look at this from the perspective of a service contract between event collection and the thing that's actually going to accept the events and do the recording, there are certain things you can do here at this layer, like that add value to the events that you may not want to. It's work that you may not want to distribute out to all the collection endpoints. So, for example, if you are collecting events that contain IP addresses, you may want to centralize the geocoding of those IP addresses in your event collection API, as opposed to having like geo IP addresses spread out all over your event collection infrastructure and just everywhere, right? So that's a great thing to do. Other candidates for kind of helpers here are anything that's, like I said, any context that's expensive to compute at the edges of your system, and stuff that you wouldn't necessarily want to try to go back and search for once you're actually consuming these events downstream. So the other really kind of cool thing you can do is you can actually start dog fooding your own API here too. So just to stick with the example of reading from the event stream, batching up these events, and then throwing them up into the S3. For example, when one of those blocks gets uploaded, you can actually send an event back to the collector that tells you when you uploaded the block, what the key in S3 is, how long it took, how big it is. So then you have another, you actually have augmented your event stream with the behavior of your event stream, kind of. So you kind of can create a feedback loop there and dog food your own stuff. And so at the end here, this is really where things kind of get exciting, and we could actually spin off probably a whole other talk. But this is where we actually get to the point where we start to analyze and do interesting stuff with our event stream. And if it wasn't clear what's happened up to this point, like we've walked through the steps of creating good events, and then having some consistent event structure across really kind of everywhere in your organization, billing, marketing, systems, all kinds of stuff. And this, structuring analytics infrastructure in this way gives you continuous visibility across all of these spaces, right? And I'd be curious to talk to you about, where your imagination takes you and where you can build some of this kind of thing if you haven't done it in the past. Many of you probably have. But on the one hand, there's some direct use here, right? Don't put the event stream directly into something like Graphite, but it is nice to, like, if you can look at a small window of data, create a little aggregation, a little bit of time series data of a bounded size. A lot of what we do sometimes at GitHub is we will actually create a little one-off Graphite database in Graphic just to kind of hack our way into using Graphite's visuals without actually loading all of our data in there. So it's kind of a cool little hack for just getting some visuals out really quick. And you can just aggregate the stream, store data in Postgres, and you can let the database do the work for you, right? And that's always a nice thing to be able to do. You can just load data into this for certain windows, and then do roll-ups, do windows, use windowing functions in Postgres. You can do all kinds of great stuff there, right? Obviously you could then kind of roll your own visuals on top of this as well. You do kind of anything you can imagine that's kind of direct use of that event stream. And then one other thing I wanted to mention too is that you can actually start, from this main event stream that we've talked about piping through, you can actually start splitting that out into other interesting event streams. So for example, you might have one stream consumer which will look at lots and lots of page view data and look at every single page view coming into your site. But you might want another stream that simply shows number of page views and number of unique IP addresses per country per hour, for example. So you have a maximum of one data point per country per hour coming into the stream from something that would have been of unbounded size. So you can start creating smaller bounded streams of information off of which other things can fork and do interesting work. So you can you take this raw event stream and you can build higher and higher and higher levels of abstraction on top of it. And so I don't really like having to end here because I would actually really like to talk about all of the cool things we can then go do with that. And we have a few things I'm prototyping at GitHub right now that actually use that kind of event stream to kind of suss out kind of some patterns in the GitHub data set. But if you want to talk afterwards about some of this stuff, definitely come grab me. But this is about all I have for now. And if you'd like to get the slides, script for the talk, and references for anything that I've mentioned, you can go to that URL, and I've got all that stuff. So that's about it.
How would you go about storing latency, jitter sort of data for something that has to happen every 20 milliseconds?
Can you say that one more time?
I mean, how would you go about storing, and analyzing latency / jitter data for something that has to happen every 20 milliseconds?
Oh, so like something that
multiple things that have to happen every.
So you're talking about this is some kind of
real-time stream.
Yeah, good question. Yeah, might have to talk about it in more detail afterwards. I'm not sure I totally grasp what's going on. But any other questions or anything? Yeah.
Quick question.
Yeah.
You mentioned a helper that you run on every box that batches and aggregates the data for the upstream.
For which stream?
For the upstream that reports to the collector boxes. This is some little daemon.
Right.
Is that like a public thing, or is that just something you guys would put together?
So it's not a so yeah. So the question was I mentioned the daemon that we use to essentially minimize latency impact on the unicorn workers that run in Ruby. And no, that's not an open source thing right now. There's no reason it couldn't be because it's really super simple. I think it's just one of those things we just have to weigh the maintenance cost versus having something. We don't want to put something out there that's not maintained.
I guess I was kind of asking if you're using like Flume or
oh, sorry.
rather than, but it's just a homegrown.
Yeah, it's just a homegrown thing. So yeah, we actually use that for exception reporting too. So yeah.